Hello friends, I welcome you in lecture number 29 on complex differentiation. In previous lectures we have discussed about complex exponential function and logarithmic function, and now in this lecture we are going to discuss about trigonometric complex functions. If you recall, we have discussed that exponential function is denoted by e to the power z, and if z is x plus iy, then e raised to z is defined as e raised to x times cos y plus I sin y. And we have also discussed that e raised to z is analytic everywhere, that is, it is entire function, and derivative of e raised to z at any point z is e raised to z itself. This we have discussed in previous lectures. Now, to define trigonometric functions, we are going to use this exponential function e raised to z, especially for defining complex cosine function cos z and complex sine function denoted by sin z. We are going to use this complex exponential function. So, complex cosine function is denoted by cos z and is defined in this way: e to the power iz plus e to the power minus iz divided by 2. And for sin z, here we replace this positive sign by negative sign, and in the denominator we write 2 times I. So these are the definitions of complex cosine and complex sine functions. Cos z is defined as e to the power iz plus e to the power minus iz divided by 2, and sin z is defined as e raised to iz minus e raised to minus iz divided by 2i. And from this you can see, if I consider e raised to iz plus e raised to minus iz, and that is 2 times cos z. Similarly, if I consider e raised to iz minus e raised to minus iz, then I will have 2 times I into sin z. And if I add these two equations, suppose equation 1 and 2, suppose I add these two, then you can see, if we add left hand sides of both equations, then this will get cancelled, and I have e raised to iz plus e raised to iz, that is 2 times e raised to iz, and here 2 cos z plus 2 I sin z, and if we take 2 common, we have 2 times cosine z plus I sin z. So 2 will get cancelled and we will obtain e raised to iz equal to cos z plus I sin z. Similarly, if we take equation number 1 minus 2, then we will obtain e raised to minus iz equal to cos z minus I sin z. So this is similar to the Euler's formula. We have seen that e raised to I theta is cos theta plus I sin theta for any real number theta, but if we replace theta by complex number, then also Euler's formula is true. Some authors are considering this formula first, and using this they define cos z and sin z. So we will remember these definitions of cos z and sin z. We are using complex exponential function to define complex cosine and complex sine, and other definitions or definitions for other trigonometric functions are similar to the definitions in the case of real functions. We have tan z is defined as ratio of sin z and cos z, which is same as the definition of tan function in real analysis. Similarly, cot z is defined as ratio of cos and sin. Sec z is defined as reciprocal of cos z, and cosec z is defined as reciprocal of sin z. These are the definitions of other trigonometric complex functions, and they are similar to the definitions in the case of real trigonometric functions. So they can ask you to write down the definitions, and you can write systematically. Here I have written, let z equal to x plus iy, d any complex variable, then complex cosine and sine are defined as cos z equal to e raised to iz plus e raised to minus iz divided by 2, and sin z is e raised to iz minus e raised to minus iz divided by 2i. And remaining trigonometric functions are written, and they have same definition as in the case of real trigonometric functions. We can simplify this in terms of exponential function also. We have tan z equal to sin z divided by cos z, and if we write definitions of sin z and cos z, we have e raised to iz minus e raised to minus iz divided by 2i, and here I have e raised to iz plus e raised to minus iz divided by 2. Let me remove this. Here I have e raised to minus iz, and this I can rewrite as 2 will get cancelled, 1 upon I can be written as minus I, and here we will have, let me write one more step, e raised to iz minus e raised to minus iz divided by I, and this is going to be 2 will get cancelled, so we have 1 divided by e raised to iz plus e raised to minus iz, and 1 upon I can be written as minus I, so this is going to be minus I times e raised to iz minus e raised to minus iz divided by e raised to iz plus e raised to minus iz. So you can convert your trigonometric function out of these 4 trigonometric functions can also be written in terms of exponential function, but all we have to remember is these two definitions of cosine and sine in terms of exponential complex function. And we can discuss about analyticity of all these trigonometric functions. For example, suppose we want to discuss analyticity of cos z, then cos z is linear combination of e raised to iz and e raised to minus iz. So using the analyticity of exponential function, we can prove that cos z is entire function, that is, it is analytic everywhere in the complex plane. We know that e raised to z is analytic everywhere, and derivative of e raised to z is e raised to z for all z. So using this we can prove that cos z is entire function. We know that cos z is e raised to iz plus e raised to minus iz divided by 2, and we know that e raised to z is entire, therefore e raised to z and e raised to minus iz are entire functions, and addition of two analytic functions is also analytic. Therefore if we add these two and if we multiply by constant, here constant is 1 by 2, or if we divide by constant, then this is also entire function, or it is also analytic everywhere. So therefore cos z is an entire function, because exponential function is entire function. Similarly, we can prove that sin z is also entire function. Sin z is also linear combination of e raised to iz and e raised to minus iz. So sin z is also an entire function. For remaining trigonometric functions, suppose I have tan z, then I have sin z divided by cos z. Now sin z and cos z are entire functions, that is, they are analytic at every point in the complex plane. Therefore this tan z is analytic at all those points where this denominator, that is cosine of z, is non-zero. The points at which cosine of z is non-zero, tan z is analytic at all those points. But we are not going into the details. we have to solve this equation cos z equal to 0 to determine all those points where this cos z becomes 0, and the points at which cos z becomes 0, tan z is undefined and therefore tan z is not analytic. But if they ask you to write down the points at which tan z is analytic, then you can write that sin z and cos z are analytic everywhere in the complex plane, and because we have cos z in the denominator, tan z is analytic at all those points at which cos z is 0. Same thing for remaining functions. Here also we can write that cot z is analytic at every point where sin z is different from 0. Sec z is analytic at every point at which this cos z is non-zero, and same thing for cosec z. So we have just introduced complex trigonometric functions, and we are not going into the details. We will just remember the definition, and they can ask you to prove that cos z is entire function, sin z is entire function. So you can use this definition, and the fact that e raised to z is entire, this makes cos z and sin z entire functions. So this is all about this session. I hope you like it. Thanks for watching.